Hello, I hope you are all well. In this lecture, I'll be talking about predictive modeling and some data pre-processing techniques that we didn't discuss before. Predictive modeling refers to knowledge discovery techniques. So we have some historical data, and based on that, we want to know what will happen in the future. Overall, there are two types of predictive modeling techniques: supervised learning and unsupervised learning algorithms. For supervised learning algorithm, we work with labeled data. It means that there is a target value and direct feedback to the learning algorithm. But for unsupervised learning algorithms, the data set do not have label or target value, and we want to find the hidden structure in a data set. I have listed some learning algorithms under each category. For instance, regression models, neural network, random forest, support vector machines go under supervised learning. And clustering, self-organizing map, and principal component analysis go under unsupervised learning algorithms. Now, I would like to discuss the four main steps for predictive modeling. The very first step is pre-processing. First, we look at data and we want to know the descriptive statistic, minimum value, maximum value, whether or not it has missing values, or if there are outliers. Then we need to decide how we want to handle missing values, how we want to handle outliers, and then we divide the data into two data sets: training data set and test data set. We use a training data set to fit your model, and then we use the test or holdout data set to evaluate the performance of your model. So feature selection, dimensionality reduction are all under pre-processing phase. Afterwards, we apply some of the learning algorithms to the data set. So there are different alternatives. Model selection criteria, cross-validation go under the second phase. Based on some performance metrics, we can choose the winning model, and then we can evaluate the goodness of that model using the test data in the third step. So we feed the test data set into the final model, and then we compare the result of the model to those of actual values. And based on that, we can evaluate the performance. The very last step is prediction. Now we apply new data set to the winning model, and we want to predict the target value. Pre-processing involves many steps, and we discussed some of them before. For example, when we were discussing pandas library, we looked into some techniques for handling missing values. We also work with Seaborn library, which is a statistical data visualization library that can be used for pre-processing. And today you are going to see some examples, including correlation analysis and clustering. But the very first step for data processing is to summarize descriptive statistics. And we know that using describe method under pandas library, we can have the descriptive statistic for all variables or columns in the data frame. So we know the minimum value, maximum value, a standard deviation, and etc. And if we have some missing values, we can use some of the methods we discussed before. But I would like to focus on outlier detection in this lecture. Outlier detection is very important, and there are different procedures to identify unusual observations. Here I have listed two commonly used techniques: box plots and z-score. Box plots are for univariate analysis. So we look at box plot for each variable, and if the data points are outside of the range, then we treat them as unusual observation. Or we can use z-score technique, which quantify the unusualness of an observation when your data follow the normal distribution. As you can see here, first we standardize data points. We subtract mu from each data point and divide it by the standard deviation in our data set. now I would like to go over some pre-processing techniques with an example. In this example, we want to analyze Berkshire dataset. This dataset is downloaded from UC Irvine repository. So there is a popular machine learning repository that you can see here, and you can many datasets are publicly available, and I chose Berkshire dataset from this repository. So as you can see here, this dataset contains the hourly and daily count of rental bikes between years 2011 and 2012 in Capital Berkshire system with some weather and seasonal information. So in this table, you can see the number of attributes or variables in the data 16, number of instances or number of observations, and also the type of attributes. They're all integer and real. And this is the univariate data. And under attribute information, you can see the brief description of each variable. For example, for season, there are 4 values because it's categorical. 1 refers to winter, 2 refers to spring, 3 summer, and 4 refers to fall. The same for other variables. For example, temperature represents normalized temperature in Celsius. We also have a temperature, which is the normalized feeling temperature in Celsius. We have wind speed. We also have the count of total rental bikes, including both casual and registered. So we are going to work with this data. So let's see how we can read this data. As you can see in this slide, first we import the libraries that we are going to use. Pandas, handling data frames, numerical Python, so we apply functions to all elements, Matplotlib library for visualization purposes, and Seaborn for a statistical visualization. So first, we need to read data from this file. So I have already uploaded this file to Canvas, and its file extension is CSV. So this is the file that you can see. The first column is date and time because it's hourly and daily data. Then for season, you can see we have 1 is categorical, 1 through 4. We have weather and we have count. And the file extension is CSV. In order to read this data in a notebook, first we need to upload this data. As you can see here, I have already uploaded here Berkshire train.csv, and then we can read data and store it as a data frame. So first we import libraries like pandas, SPD, numerical Python, is NP, Matplot for visualization purposes, and also Seaborn that we are going to use today. Now I define a variable named train, and now we want to read all data points in that Excel sheet. So PD I call pandas, and the method that we use is read underline CSV, and then we pass the file name, which is Berkshire train.csv. So let's run it. Then everything is recorded as a data frame in that variable. So you can print this. So it's a data frame. There are different columns and different rows. So more than 10,000 rows and 12 columns. Okay. After we read the data with just one line of code. Now we want to look at the descriptive statistic. As I mentioned before, this can be the very first step for data pre-processing because we can get an idea about the variables, the attributes in the data. And it's very simple. We apply the describe method, and then we can see the descriptive statistics for all columns in the data frame. Okay. So let's print train dot describe so you can see count, number of data points, minimum value, a standard deviation, maximum, average value, 25% quantile, and for example for season you can see the minimum value, maximum value, so it's categorical. For holiday, working day, or weather, temperature is a real value, and you can see that there is no missing values. The count, the number of observations for all variables the same, and you can see the variation in each variable by looking at the standard deviation and the maximum value. So after we look at the descriptive statistic, which is a univariate analysis, then we can look at the bivariate analysis techniques. So we want to understand data structure, right? The relationship between variables. We can use pairwise relationship using Seaborn library as a pre-processing technique. So it generates a pair plot, so technically evaluates all pairs of variables, and then you can look at the histogram, you can look at their scatter plot and the relationship. So we call Seaborn library dot pair plot, which is a method, and then we pass the variables that we want to look into. So the relationship between temperature and humidity and wind speed, and etc. So let's run it in a notebook file and you can see the results. It's a great visualization technique with one line of code, and we can extract different pieces of information. So it's pair plot defined under Seaborn library, and then the variables, let's say, are temperature, humidity, wind speed, a temperature, and count. So it's still running. And here is the result. So here you can see the histogram for each variable and also the scatter plot between each pair of variable. For example, here you see the scatter plot for temperature and count, humidity and count, and at the end the histogram for the variable count. And if you look at the scatter plot for a temperature and temperature, you can see that there is a direct relationships, and there are some data points over here which do not follow that direct relationship. Or if you look at the wind speed, you can see the histogram here, and look at the relationship between wind speed and a temperature or count. There might be some outliers or unusual observations, or over here between wind speed and a temperature, this data point stands out, and that's how you can understand the relationship between each pair of variables, the histogram, the distribution for each variable, and understand the data structure with just looking at one graph. So to understand data structure, we might want to look at pairwise correlation. So we want to know the correlations between each pair of variables, and we can look at heat map actually to discuss a correlation, which provides a clearer visual for large data set. Also, we can look at hierarchical clustering, which orders data by similarity. It's like a dendrogram. And all of it can be produced by cluster map method under Seaborn library. So seaborn.clustermap, and then you pass the variables that you want to look into dot correlation. Then it produces the heat map and also the correlation between each pair of variables. Let's implement this in a notebook and you can see the result. So again, we call the Seaborn library. This time we use the cluster map method, and then we pass the variables like temperature, humidity, wind speed, a temperature, and count variable. Then we want to look at the correlation dot CORR, and let's run this. And this is the graph. So here you can see the color bar, and it shows the correlation between variables, heat map, cluster. If you look at, for example, the A temperature and temperature, you can see that they are hardly correlated, almost close to 1. And for example, between the wind speed and humidity might be a negative relationship based on this color map. And also I would like to draw your attention to the dendrogram here. So you can see that it orders variables by similarity. So the very first A temperature and temperature can be grouped together. So that's the very first level you see. And then we can add the third variable count to that group, and that's why we call it hierarchical clustering. So with this, you can identify variables which are highly correlated or not correlated at all. Okay. So far we talked about descriptive statistics and some correlation analysis, like a bivariate data analysis. Now I would like to talk about outlier detection using z-score. So the way that it works is to standardize data and then compare it to a threshold. So when we work with the normal distribution, we know that almost 97% of observations fall between plus minus 3 standard deviation. So 3 can be the threshold. So if the data points are in the tail of the normal distribution, we can treat them as outliers. So to do that, we can define a function which normalizes the data first and then returns outliers in a list. And that's what you see here. So we first define an empty list outliers, then we define a function named detect underline outlier, and then there is one input argument which can be a list. Then we define the threshold. So if it's more than plus minus 3 standard deviation, then we want to treat them as outliers. So to do that, first we need to standardize data. So first we calculate the average of our data point. So here you can see we use the numerical python.mean, and then we pass the data as the input. Then we store it in variable mean underline 1, and you can define any other variable that we want. And then by applying the standard function under numerical Python, then we calculate the standard deviation, and we write a for loop. Now we write a for loop to go through all elements in the list. Okay. Then we standardize them. So I define a variable named the underline score. We subtract average value divided by a standard deviation. And then now we have the selection statement. If the absolute value of z-score is more than threshold, then we add it to the outliers list using the append method. And at the end, we return outliers. So if we don't have any return statement in our function, then we are not able to see the result. Now let's define this function in a notebook and apply it to one of the variables in our data set. So first we define an empty list, outliers, then a function. We name the function detect underline outlier. There's one input argument, let's say data underline 1. Forget the colon. Then we define a threshold, which is 3. We define a variable mean underline 1. Again, this is an arbitrary name. So np.mean applied to the data. So we calculate the average value, then we calculate the standard deviation. And then we write a for loop to repeat this process for our data points. We calculate z-score, which is that data point minus the mean value divided by the standard deviation. Now we can compare it to the threshold value. So if np dot absolute value abs is greater than threshold, then we add it to the list of outliers. So outliers dot append. Then at the end, we have the return statement. We want to return the list of outliers. Let's run it. Again, this is a function. If we want to see the result, we need to call it. Say detect underline outlier, and I can pass one of the variables of Berkshire data set. Let's look at the wind speed. Okay, there is a typo here. Let's run it again. Here we go. So you can see that there are many outliers in that variables, and we kind of expected that, because when we look at the relationship between wind speed and other variables, some of the observations are far from the majority of data points. And if we use the z-score, you can see we identify several outliers. If we want to know the number of outliers, we can apply the len function because it's a list. And then you can see that 67 data points are identified as outliers for this variable. Okay. Now, one technique is to remove outliers. And this is a very quick and dirty way to handle outliers. So let's say if you want to remove outliers, this 67 observations, and we define a list which doesn't have the identified outliers. And here you can see the example. So I have a variable final underline list. So here we define a list and some 4 variables and a selection statement. Now we want to keep all x values which are less than the threshold, so less than 3. Then that becomes our final list, and if they don't meet this condition, then we treat them as the outliers. So we can quickly implement this, and you can see the final list. So final list for this variable if we want to remove all outliers. And you can see I'm defining the for loop and the selection statement inside the bracket. For x in train wind speed, if the standard value x minus the mean value divided by the standard deviation for the same variable, train wind speed, is less than 3. We'll keep them. Okay. Seems that there is a typo here. We close the list here, so we don't need this 3, and let's run it. Okay. Now we can look at the number of items in the final list. So 10,819, and if we compare it to the original number of elements in wind, train, the wind speed column, there is a typo here if you run it. So originally we had 10,886. Now if we remove 67 outliers, we end up with 10,819 data points. So that's how we can use z-scores to identify outliers, and if we want to remove them, we can apply the same condition, just keep observations which fall within plus minus 3 standard deviation, then we remove the identified outliers. Now, with that, I wrap up our discussion about data pre-processing techniques, and would like to introduce the new library in Python that we use for both supervised and unsupervised learning algorithms. Scikit-learn library provides a range of options for both categories. Scikit-learn library is built upon the scientific Python package that must be installed before we can use scikit-learn. Here's the important part. Scikit-learn library is focused on modeling data. It's not focused on loading, manipulating, and summarizing data. And for those features, we use numerical Python and pandas libraries. So everything we discussed in this lecture for data pre-processing, we just use pandas or numerical Python or Seaborn. So we didn't use any methods defined under scikit-learn library because the supervised learning and unsupervised learning algorithms are focused on modeling the data, not manipulating or handling missing data, for instance. So in the next lecture, we focus on regression models and scikit-learn library.